last time I promised that we will prove the existence of Campbell-Hausdorff series, but the clue observation is that differential of exponential has pretty nice formula. And so first, let us obtain this formula. So I start with the following lemma. So let me define the following map. I should rather consider it as a series. So it is 1 minus e to the negative s over s. Okay. So then for every x and y in Li algebra G, we have the following formula. Well, our goal is to compute a differential of exponential map at any point x. Okay, but I will. So differential of exponential map it's something from the tangent space of this vector space, which is Li algebra. So from Li algebra itself, right? So I need to compute something like this, where y lives in G as well. But I would like to do it in terms of just commutative, like Li brackets, right? So far, this thing does not live in tangent space at identity. It lives at tangent space at x. Well, I should rather say a tangent space at x, right? So I should shift it right back. For that, I use left multiplication and shift it back to G. Then the formula is like that. So it's a series, so it's a linear operator, right? Such that I add x into this series. Okay, let's prove this. All right. So let me consider the following curve on x, on G capital. Well, I will need to compute something like this, and something like this will be tangent space to this curve at t equals 0. So I will need exp negative exp x plus ty. So let me consider this, and so for some reason, so the trick is to rewrite it as follows. It's x negative x over m. So take some natural number m. So it will be like this, times exp, right, x over m plus t over m, y, everything to the power m. I just did nothing. I just used the fact that exp of x plus y is exp of x times x of y if x and y commute. right? So of course something commutes with itself, right? So I apply this m times, right? Then I look at left-hand side of this. So I don't know, let me call this, I don't know, star. And so left-hand side of star, it is exactly tangent vector to gamma at t equals 0, right? But then I do the following. So let me write down. I say that this is, so let me first write the formula, and then I comment what's going on. First, let me, so this is also some curve in G, right? So let me denote it as gamma m of t, just a notation. So I claim that if I take tangent space to this thing, it will be computed as follows. dl gamma m of 0 to the power negative m, then sum over k from 0 to m minus 1. So what I'm doing basically here, I'm just applying Leibniz rule in a kind of sophisticated way. So I differentiate a bunch of the product of things, right? So of course you know what is the Leibniz rule or product rule for functions that have values at, in I don't know, in numbers, right? So here I have values in G. So I need to, be accurate what I mean by Leibniz rule. So first, let me write down the formula. So it's dl gamma m of 0 to the power m minus k minus 1 dr gamma m of 0 k, and then gamma, all this applied to gamma m prime of 0. Okay, so this is an consecutive application of what I said Leibniz rule, but more precisely, let me just formulate it for two curves. So suppose I have two curves, gamma 1 and gamma 2. So and then I form a third one, which is gamma 3 of t. It's just gamma 1 of t, gamma 2 of t. So these are curves in G. So they take values in G, right? And so therefore I can multiply just pointwise. All right? Then I say that gamma 3 prime at 0 is, so Leibniz rule, usual Leibniz rule says that I take derivative of this times this plus derivative of this times this, right? In correct way, it is restated here as follows. So I take derivative of this, right, times this, but I mean derivative of this is tangent vector, and multiplication from the right, I need to take derivative of differential from the right by gamma 2 or at 0. Gamma 1 prime at 0 plus, so take derivative of this, and I have to multiply by this from the left. So dl gamma 1 of 0 gamma prime 2 of 0. So this is a statement. I give it to you just a statement, and to prove it, it is exercise. But this is just Leibniz rule in case of Lie groups. Okay? And then I apply it a bunch of times, I get this, right? Because I pick a term here, right? I say k term, right? By the way, yeah. So in total, I should have m. So this plus this should be m minus 1. So yeah, works, right? So I chose 1. I have k others on the right, and m minus 1 minus k, these things on the left.
Don't we need a binomial coefficient?
Don't we need binomial coefficient? No, we don't. We just, combinatorics here is pretty trivial. We just pick it's every choice is already here. Yeah. Okay. And then this one just comes from this one. I just need this to combine with this one. Right? Hi. So this is by Leibniz rule. Which is this double star. And this is double star. And I offer it to you as exercise. Okay. Right, so I have negative m here, which cancels with this m, right? So basically what I can continue, so this equals to, right. So this equals to the following. Let me rewrite it like this. Sum over k from 0 to m minus 1. And then d L gamma m of 0 to the power negative k. Then dr gamma m of 0 k. And then dl, so I have, so this m cancelled with this one, and what I have negative k there already, and left and right actions they commute, so I can move one to the right actually. So therefore I have one inverse dl inverse left, and all this applied to gamma prime m of 0. So this guy is a differential of conjugation by gamma m0, right? To the power k, right? I multiplied on the left by gamma m0 inverse to the power k, and on the right, right? So this is a differential of conjugation by gamma m to the power k, which is at capital, right? So therefore, I can write it like this. Sum over k from 0 to m minus 1 at so at is conjugation, so g something g inverse, right? So I really should take to the power negative k here. Right, gamma m of 0. And then what's left is this. So all these are invertible, by the way, things, right? So therefore I can put minus here. It makes sense. Of this. Okay. So first, and then I use functoriality of exponential map. Right. Well. So remember that we had this that at so this is gamma m of 0. So we should remember recall what is gamma m. Gamma m of 0. So here's the step. What it is? It is exp of x over m, right? So I have here at exp, right? Add exp of x over m, and this is actually e to the small at, right? X over m, right? Well, this m it's just a number. I can move it to here, right? And if I put, so this is just side computations. If I put negative k here, so I have negative k here. So this is e to the negative k over m add x. So let me use this now. I continue. So it's sum over k from 0 to m minus 1 e to the negative k over m add x applied to this thing. I think I lost minus 1 here. Gamma m of 0 of gamma m prime of 0. Okay, very well. So now let us see what, so I think I need one more parenthesis here. So what is this thing? I claim that this is actually just y over m. So I claim that, well, I claim that this is y over m plus something that when m goes to infinity behaves as 1 over m squared. Okay, so this is what I claim. Let's see why is that true. So we're checking this. So I need to consider exp, right? What was gamma m prime of 0. Right. So, right. I need, so gamma was this, exp, so gamma m, right? And then x over m. So this is gamma m. Right, okay. So x over m plus y plus t over my. So this thing is gamma m. Then I multiply by this on the left, right? And then take derivative with respect to t. But this thing I can rewrite as follows. It's just our rule. How? So no minus here, by the way. It's just this. So it's our rule how we multiply, how we Taylor expand multiplication, right? So I will have linear terms. So this plus this, which gives me just t over my, right? So it's x of t over my plus quadratic terms in this and this. But this is something that I hide in O of 1 over m squared. So when I take now derivative with respect to t, well, of course, t is also here as well, right? But when I take derivative with respect to t, I need to see what are linear terms. So I will have y over m plus something here, which is multiplied by 1 over m squared in any case. So I have this, right? So therefore, so dl inverse gamma m of 0, gamma m prime of 0 is t is just y over m plus o 1 over m squared. Okay, so let me now again continue this. So what happens now, remember what I started with. I started with gamma prime of 0. It had no m's at all. So I can take any m, right? So I can as well just put limit here, as m goes to infinity. If this limit exists, but we're going to prove that it exists, okay? So I would like to insert limit. And then sum over k from 0 to m minus 1. And then I have what? So okay, let me rewrite it. E to negative k over m, add x, right? Y over m plus O of 1, O capital of this. Okay. Then I would like to write it as a sum. So I will have limit as m goes to infinity, 1 over m sum k from 0 to m minus 1 e to the negative k over m, add x is here, y, applied to y. This 1 over m I just moved outside because this is just some linear map. So I can move it through linear map. Okay, and then plus, what is left? Again, limit as m goes to, again, we need, always, as mathematicians, we should check that all these limits exist, but we will, at the end, we will see that they do. So the thing is that we have limit m goes to infinity of what? So I have something like this, right? So I have expression of the same kind with maybe some other y, something else, not y, but maybe some z, right? So let me write it like this. So 1 over m sum k from 0. So what I'm saying is that this is actually some I don't know, z over m squared. 1 over m I put here, so sum, and then the same expression I just change y to z. E negative k over m at x applied to z, but another 1 over m is left, right? So this times another one over m. So the thing is that if we see that this limit exists, then this limit is 0. It exists in 0 because, then this exists and limit of this is 0, right? So this is 0 if limit in the first term exists. Okay, so we need to see that this limit is what it is. But now look here. So I claim that this is it's Riemann sum of e to the negative st dt, right? Where s is at x, right? So let me write this down. Well, let me denote this as, I don't know, a, and a is actually then integral from 0 to 1 e to the t at x dt applied to y. Again, this is some series, right? And we integrate series and get series as well, right? So actually, if we integrate this, we'll get exactly what's written over there. So it is f of at x.
Isn't it e to the negative?
Yes. Yes. Right. So if we integrate, we'll get exactly what's written. Okay? Mm-hmm. That's it. So I think this is one of the most. You can avoid it during lectures, but I think this is one of the cores in the relationship between Lie groups and Lie algebras. And also on this conference that I was last time, I learned that so actually this can be inverted, right? This series that starts with 1, right? And this will be s over 1 minus e to the negative s. And this is called actually Todd series. And this arises in on the conference. This appeared in Riemann-Roch theorem. So when you try to
Please remind what's Riemann-Roch theorem about.
It relates analytic conditions on some complex curves, dimension of meromorphic functions with poles or zeros on some divisor, and then the genus of your complex curve. And so you have like an geometric data and analytic data, and you want to relate it. And of course, your analytic data is kind of global, so you can study it with with the help of some with the help of K theory. And so when you try to relate K theory and just usual cohomology here, you would need you can send anyways, to make the two series work together, you need to twist everything by this dot series of Euler class of your anyways, so I'm kind of go deeper than I want, but surprisingly, this has like a very deep connection. Okay. Anyways, as a corollary of this, we get. So we never stated that exponential map is holomorphic, right? So now we know this because so let me state this. If I take what it means that if I take differential of exponential map applied to IY, where I is just root of -1, right? Then I can factor it out. Dx exp of y. This is just because add x, right, is C-linear, right, if I have complex manifold. Add x is C-linear. So therefore, differential of exponential becomes C-linear as a series of in a C-linear map. And so therefore, exp is holomorphic. In particular, you can generalize theorems, 3 fundamental theorems, to complex Lie. So you can just restrict them for complex Lie groups. Of course, you need for theorem 1 you need a little bit more. So we'll have almost complex structure, right? To make it like complex structure, you need like some you need some more general theory that we're not going to. But the fact that exponential is holomorphic is kind of crucial for us if we would like to state these theorems for complex case. Okay, so from now on, let us just assume that all these theorems they all also work in complex case. Okay. All right. But all this story started with our wish to prove the following theorem that I stated last time. Okay, let me state it one more time. So this is, we call it existence of Campbell-Hausdorff series. And it goes like this. So for sufficiently small x and y in G, define another element in our Lie algebra as follows. So I just take e to the x, e to the y, right? Since they are small, this is exponential of something, and this something we denote by z, and this is a function of x and y. Then if we try to expand it as linear, as a Taylor series as a function of x, y, so then what we get is Lie series, and this is the statement of theorem, right? So define this, then the Taylor expansion of z is a Lie series. And what it means, we also discussed last time. It means that all terms are given as a bunch of commutators, right? So it means that z of x, y, you Taylor expanded, it will be sum of terms of this sort. So you have x, y, and then you apply commutators of x bunch of times, and then commutators of y bunch of times, and so on. And then x and y, and you stop at some point. And then you take, maybe it has some just coefficient, which is just complex number, or I don't know, real number if we have real Lie algebra. And I need to close it here. So this is by definition what is a Lie series.
And again, we will take a sum over all the commutators, right?
What does it mean over all commutators? So So what I claim is that it is a sum of terms of such kind. Right. Well, you can also say the following: that okay, you take y, and then you take commutator with x r1 times, commutator with y s1 times, then commutator with x r2 times, commutator with y s2 times, and so on. So you fix the word in r2 and r1 s1, and you know, sum over all ri's. And this will be, yeah, you sum over like the length of word in ri's and over all ri's. And well, of course, you will have a lot of things, but in many cases you will have 0 in your coefficient. So okay, let's try to prove it using this. That our formula for dx of x. Okay. So we start with the following. So proof. Let x of t be some smooth curve in G now. Okay. And then, well, then let me denote gamma of t. It is to be e to the x of t. So exp of I kind of interchange e and exp, but this is just curve in a group now. All right. So let me now consider gamma prime at some t0, at some fixed t0. So let me actually take gamma. So let me take gamma tilde of t to be the following. It is e to the x of t0 plus x prime of t0 t. I just need these two terms, actually, in my x of t. Okay? Then I claim that gamma prime of t0 is the same as gamma prime of 0, right? Do you agree, Vadim?
I'm trying.
Let me wake you up. Okay, so just look at here and say, do you understand that or not? And if you don't, say I don't, then I explain it.
Looks okay.
Well, it doesn't because I have tilde here. It's not on purpose. Sorry. Yes. Now it's okay. So when I compute tangent vector, I just need these two terms in here, right? So very well. Then I would like to see the following. So dl exp. So let me actually denote this to be x0 and this to be, I don't know, v0. Physics. Oh, okay, not v0. y0 for some reason. Okay. So this is speed. This is coordinate. Okay, and so I would like x negative x0 gamma prime at 0 here at t0. So I claim so this actually is f of add x0 applied to y0. So this follows just from our lemma, right? In our lemma, we say let us reiterate it. So basically, I had what, e to the x plus yt, right? And then I applied e to the negative x, and then I considered d over dt of this at t equals 0. So this exactly what I was doing in lemma, right? I took this, right, and then shifted, and this is my dl of my gamma of t, and we computed that this is actually f. This is like inverse of our taught series, whatever, x applied to y. And since my gamma prime of t0 is the same as gamma tilde, right? My x, this is my x in this formula, this is my y in this formula. And so I just compare and I get this. Okay? Okay. Lemma. This was lemma. All right. So now let me fix like in theorem x and y in G, right? And let me consider gamma of t to be e of x, e of ty. And this is some, so if my x and y are fixed, I define function of t like this, and if they are small enough, right? If they are small enough, then z of t is a well-defined function on. I actually would like it to be on 0, 1. So 1 will be if x and y are small enough. Okay, this will be my curve x of t. This will now is z of t, right? And so okay. Then I say what? dl of exp of z of negative z of t. This is just application of this thing, right? So t now is my t0, and I take derivative around t, right? So this is actually x0, this one. And then of gamma prime of t, so I kind of replace t by t0 by t. Sorry, what? Yes, gamma is this one, is this guy. Equals f of at z of t applied to y. Well, sorry, y, it is what? It is z prime of t, actually. It's derivative. Right? So this is just application of this thing. All right. So what I need next is that this thing, so first observation is that this is just y, our fixed y. Why is this true? Let's check this. Yeah, okay, so why is this y? So what is going on? I take z of t is this, exp of negative, so I take gamma prime of t, right? So I will get ex t plus s. So this is actually, so this is simple. So let me just write formula. So this is gamma of t plus s, right? And then I apply dl of exp minus zt. So this will be ex e of ty inverse. And then take derivative with respect to s at s equals to 0. So this is exactly what's written in here. So if you just look at what is gamma, right, and how to compute its derivative of t and shift it by dl. So this is exactly what's going on. Okay? But then this is easy. Now, so inverse of this, e of x goes to the right and kills this e of x. And then I have e of ty, which kills this e of t. So this is just d over ds e of sy, right? At s equals to 0. But this is just y. Very well. So this is y. Now, I have some series in z of t, and I have z prime of t. So what we are doing, we are, so you say that a lot of times, we are obtaining a differential equation on z of t, which will solve in terms of series. Okay, so this thing can be inverted, right? It is a series that starts with 1, so therefore I can invert it as a series as well, right? It's actually it will become like a dot series, like honest dot series. So therefore, I have the following: z prime of t is f inverse of add x of y. So x is what? X is z of t. So we're almost there. So we just need to work with this thing a little bit. So I have e. So let me write it like this: e to the add z of t. So let's first look at what this thing is. I apply functoriality of exponential map. This is add, right, of exp of z of t. Exp of z of t is this. So this thing is actually add exp of x add exp of ty. But this thing is now, then let me go back and apply functoriality of exponential again. This is e to the x, e to the add x, right? E to the add ty. Okay, sorry, add ty. So so if x and y are small enough, right? Add z of t is small enough. Like z of t is small enough. So anyway, so I don't want to do anything with norms of linear functions, but anyway, so if we're close to 0 in some usual sense, right? I can write down add z of t as series, which is actually a logarithm of this e of add x, e of add ty, right? So this is series in add x, add y. And I don't know, and t. T can be factored from here to here, right? So let me denote this so what we got, so let me denote this series to be, I don't know, L of add x, add y, and maybe t. So what happens now is that I have z prime of t is f inverse. This is series. This is just composition of series applied to y. Now we actually can integrate, integrate series, right? And then I will have z of t, just integral of f inverse of L of add x of add y of t applied to y. And then I can take t equals to 1. So I will get z equals to integral of f inverse of L of add x, add y, 1. And all that applied to y. So we're done. So what our goal was to present Z as a series in add X and add Y. This is exactly our goal, and we did it. Applied to Y, of course. Yes. Okay. Yeah. So this is. Yeah. So if you calculate the integral, you can get explicit coefficients in this series if you wish. If you look in books or even in Wikipedia, you will see this expression, for example, and an integral of inverse of this f of logarithm.
This proof is very similar to the Campbell-Hausdorff formula.
I mean, this is Campbell-Hausdorff formula.
Yeah.
Just I don't like coefficients are just some well, you can express it combinatorially or through this function.
You have thinking formula.
I have yeah. I mean,
It's terrible.
yeah. All explicit formulas are quite terrible, but you don't need them. The most important part is that you have the series, and so you don't. If you try to compute ex and ey, you will get e to the z, where z is again in your Lie algebra. So because your Lie algebra is closed under commutators. Okay, so this concludes our maybe first half of fall semester, and now we start talking about representations. Okay. So if you completely lost, you can now wake up and just enjoy some definitions without proofs. So we proved almost everything except maybe Edo theorem, but also it's quite hard to prove. All right. So representations. Of Lie groups, Lie algebras. Definition. A representation of a Lie group G is okay. So for Lie group, I would like it to be finite dimensional. Vector space V together with Lie group homomorphism. Rho from G to GLV. That's it. So let us also introduce some terminology. We will say that that on V we have an action of G. It's the same thing. It's the same piece of data. Also, sometimes people say that okay, V is a representation of G. It implies that we have this homomorphism already, right? Sometimes if it's clear what it is, then corresponding homomorphism we just denote as rho v. Okay. All right.
GLV is the same as we, for example, call it endomorphisms.
No, inversible.
Oh,
So these are all inversible linear maps of V. That's it. Yes. Examples. Okay, so this is where you can help me. So feel free to offer. What would be an examples of representations?
So Fourier, like Fourier functions on the circle. Exponentials on the circle.
It is a representation of what?
Of U1.
Of U1. Okay, very good. Yeah, adjoint. Yeah. So this one is it's not very good because it's not finite dimensional. What you said, right?
Yeah.
We have such construction, yes. So, but okay, let me start with adjoint capital at, right? So this is so my V is in this case.
The group will.
Yeah. So this is G, right? In this case, and G. So if you take my rho, it looks how rho of G is D CG, right?
There is also like you can. I forgot how it's called, but when you construct the group algebra and you just act on every element of
group algebra
on
what?
every basis element from the left with an element of a group, you obtain a representation which contain in finite dimensional case it contains all irreducible representations.
Your group algebra is finite dimensional if your group is finite.
Yes.
So this we don't have finite group except if in some very degenerate for us cases, right?
But you can say that you have given basis on the, you can construct the basis.
Eigenbasis of what?
Gamma basis.
Okay, so right, so all this is doable, but let's start with something simple. So this is simple enough, and this is something that we saw already, right? But also, I mean, just take GLN, right? It acts on Cn. So this is, and sometimes we'll write like this. GLN, it acts on Kn, right? Where K is depending on whether it's GLNC or GLNR. And also all matrix Lie groups, they act on Kn. So this is the first example.
L2 functions on the sphere, they form a representation of SO3.
That's true, but again, so let us. So we need this to be smooth map between manifolds, right? And in case of L2, this will be like I don't know, diffeomorphisms of your. I mean, you need really this to be finite dimensional. So you're trying to give me some examples when this is. It's hard to define what is this homomorphism. It will be much easier for Lie algebras, and we'll do this. Right? Lie algebras, so everything is algebraic, and so you will need only. You don't need V to be finite dimensional. Okay, but still, it's good examples, but they are too hard for us at this stage. Okay. What else?
So group C now, can we consider?
Act where? Sure, SL2 act on K2, right?
Yes.
It's as I said, all matrix Lie groups. So everything inside. So if I have G, which is inside here, it also acts on Kn. And in general, if I have a homomorphism from one group to another, and I have representation of the second group, then I have representation of the previous one. For example, I don't know, I have SU2, right, which is which of course has representation in C2, right? But also you have SU2, maybe I don't know 3. It's universal cover of SO3, R, and this acts on R3. So therefore SU2 also acts on R3, right? Since I send SO3 to GL3, I can of course compose it with this map. I send it to GL3 as well. Okay, so these are first few examples, but what's important is that we actually can create a lot of new representations out of old ones. So if you give me, and I can do it by direct sum or tensor product, and so let's discuss how it's done. So suppose I have so two representations. Sometimes I will give representation as a pair, right? Homomorphism, vector space. So these are representations of G. Then I just define, well, rho on V1 plus V2 of G it's just, this is a linear transformation of V1 plus V2, right? And so it should act somehow on a sum of two vectors. U lives in V1, V lives in V2, right? Well, and this will be just rho V1 of G acts on V plus rho V2 of G acts on on U. This is on V. This is very easy. Also, we can define an action on tensor product. So you have, let's define it on such thing. And this is also easy. It's rho V1 of G acting on U, tensor rho V2 of G acting on V. So, and it's very easy to check that this is homomorphism of Lie. So these rows are homomorphisms of Lie groups. Okay. So then rho V1 plus V2, V1 plus V2, and rho V1 tensor V2, V1 tensor V2 are representations of G. What else can you do with the representation? So you can sum, you can tensor. What else?
Take the dual.
Yes, take the dual. It's the most next natural thing. And we do have this. So let's write down explicitly what we do. Very well. So if I take rho V, right, Yeah, by the way, here I write v1, v2, right? So here maybe I should do it like this. And here also row v, it's a representation again of G. Then I defined row v star of G. So it should act on linear functionals on V somehow, right? Should act on F. And by definition, so this is again definition, rho v star of G. So this is another linear functional, right? We define it by its action on vector V. So this V lives in V, right? So this is just F of rho V of G inverse V. So in any case, so if you think of, for example, matrices, so this is just usual representation is a multiplication is you multiply from the left, right, matrix by column vector, right, and if you think of linear functionals as row vectors, right, you multiply from the right, but this is anti-homomorphism. Then you have to twist it by another anti-homomorphism, which is taking G inverse. Okay. Yeah. So I am saying that you can naturally think of elements of V as column vectors, right? Then elements of V star are row vectors, and you pair them just by by multiplying. It's just dot product then. Yes, and then you can, of course, how do you act on row vectors? You multiply on matrix from the left, right? Say by GLN, right? So this is some matrix, and so this is multiplication by matrix from the left. So if this is a row vector, you multiply by this thing from the right. Well, multiplication from the right is anti-homomorphism. It's a right action, but we need left action actually here. So you twist it by this G inverse. It's always like in representations, right? To define the dual representation, you need some natural anti-homomorphism on your group or your algebra, right? Like in a language like of Hopf algebras, it's called antipode.
Anti-how?
Antipode.
Ah.
Yeah. All right. So let us continue. Next natural definition is that what is homomorphism of representations. So definition. Let row v1, so maybe again row 1 v1, row 2 v2 be representations of G. Then a linear map, say phi from v1 to v2 is called homomorphism of representations if following happens: f of G rho 1 equals rho 2 phi of G for every G in G. In which, yes. All right. So then we have two representations isomorphic, right? If phi is an isomorphism, if it's a homomorphism of representations, and this is isomorphism of vector spaces. All right. So now let us discuss briefly what are representations of Lie algebras. Well, again, definition just goes completely in analogy of representation of a Lie group. So a representation.
In what definition? Maybe there should be V instead of G.
Where?
In one definition, because
So here
no, we have phi of G, but phi goes from V to V, from V1 to V2.
sorry. Yes. So here I am wrong, of course, because I have to put G in different place, right? Yes. Thank you. So I have to put G here. Rho 2 is G, and that is a linear transformation, and phi is linear transformations already. Yes. Phi rho 1 of G. Thank you. So representation of Lie algebra GL, Lie algebra G is a vector space, and I don't really want it to be finite dimensional, together with okay, I'm running out of chalk. But anyways. Together with homomorphism of Lie algebras, G, so rho, G to GL small. Okay. Very well. So this definition, and of course, like all these examples that we had before, we also have it here, right? Because if you have rho v, so I don't know, observation. If you have, this is a representation of a Lie group, then this is a representation of the corresponding Lie algebra of G, which is Lie algebra of G, right? So if this was homomorphism of Lie groups, this is homomorphism of Lie algebras. Moreover, every finite dimensional representation of Lie algebra is actually a representation of some Lie group, right? As we learned of actually some simply connected Lie group, right? This is just because of second homomorphism theorem, right? So all finite dimensional representations of Lie algebras, they are actually examples come from representations of Lie groups and that way around. What about infinite dimensional presentation? Some example of infinite dimensional presentation. Okay, Heisenberg algebra. Right, so you have x, y, z there, right? So maybe examples of infinite dimensional. They go to d, then I don't know, du, u, maybe with some coefficients here, and maybe 1. Right, and this acts on somewhere, on polynomials, say in U. This is infinite dimensional. Oh, of course, you can form infinite dimensional sum.
What about if you get a Sorrow, for example?
Yeah, so we have, of course,
Algebra itself is infinite.
it's infinite dimensional, so that's okay. It does have infinite dimensional representations, of course. No, the most fundamental one we'll learn then with Lemma modules. I don't know, like or Fock modules, which is more, I guess, right word for physicists. Yeah, so, but also SL2, for example, remember, we had this that I don't know exactly, but it goes to d over d SL2C, I mean. D over dz, I don't know if we, yes, we had this in seminar. D over dz, then z, d over dz, z squared, d over dz. So algebra generated by this. And this acts on, again, say on polynomials in D, which is infinite dimensional.
But when we say about, so when we say about infinite dimensional vector space, we don't demand any functional analysis stuff, yes?
No. So that's the whole point of why I am okay with saying infinite dimensional in Lie algebras. There's no analysis here. Yes. Okay. And the last thing I would like to do is just to write. So again, we have if I have two representations, I can form sum, I can form tensor product, and I can form dual representation. So let me just give you formulas how it works, which you can of course deduce yourself. But okay, let's put it on board. Yeah, so what I would like to see that suppose that I have these are representations of Lie algebra G. Then again, well, for just direct sum, it's just the same formula as we have for groups. What about rho v1 plus v2 then? How it acts? Sorry, direct sum I said it's the same tensor product. So I take u tensor v. So this is okay. We put it as a definition. So this is just rho 1 of g of u tensor v plus u tensor rho 2 of g. Maybe g is not the best. Usually it's element of group. So I take element of an algebra, right? Applied to v. So x here. So, and I have to put x in here, right? So x for any x in G. And also, again, if rho V representation of the algebra G, then I can define rho V star as follows. It acts on F, gives me another functional that I compute on V, and this is just F of rho of minus x here of V. So antipode in Lie algebras case is putting minus. Of course, they are all related by exponential map. If you take inverse in the exponential, and on Lie algebra level, you get minus, of course. Then, so the statement that is that if we define it like this, then we have representations of Lie algebras. I mean, exercises to check it, but also you can see that if I take a representation of Lie group, take a derivative differential of the corresponding homomorphism, that's exactly the formulas that we will get. Okay, so this is consistent with Lie group structure on the tensor product and dual. Okay, so I guess we will end our lecture here.